Bismillahirrahmanirrahim. Assalamu alaikum. This is the third lecture in chapter 2, which deals with evaluating properties of pure substances in Thermodynamics 1 course for Fall 2020. Earlier in this chapter, we talked about phase change of pure substance from liquid to vapor, to superheated vapor, and how to use the property tables to find the properties of pure substances at different phases. Today we'll move forward and we'll talk about how to deal with ideal gas and to find the properties, mainly the PVT, pressure, specific volume, and temperature. And also in this lecture we'll see how to also from these properties we can find also the internal energy and enthalpy of ideal gas and incompressible fluids. So there are several many equations that are proposed to find the relation between pressure, specific volume, and temperature for gases. And these are some of the relations. One of the well-known relations is the van der Waal equation of state, and here or in this equation the intermolecular attraction forces and the volume occupied by the molecules are taken into account, are two factors that are taken into account, which are not taken into account in the ideal gas equation that we are going to use in this chapter. Ideal gas model is an ideal model, okay, which means that it has many assumptions. For example, in real gases, although the intermolecular forces are very small, but they are still there. But in the ideal gas model, we assume that these intermolecular interaction, okay, forces are not there. And here this shows the ideal gas law assumptions, all of the assumptions, or all of the main assumptions. So we see here, for example, that the volume of the individual gas particles is negligible compared to the volume of the gas itself, and the collision, okay, has no effect on the kinetic energy of the molecules. Very important one: no forces between the particles, so the intermolecular forces are not there. The only important energy of particles is the kinetic energy, so no potential energy, and the temperature is proportional to the kinetic energy of the particle. Okay. So those were the main assumptions for in the ideal gas model. The ideal gas models, I'm sure the ideal gas equation, I'm sure that you did deal with that in earlier courses, maybe physics, and there are many forms. The form that we are going to use in this course, the main form is this one: PV equal mRT, pressure, V is the volume, M is the mass, R is the gas constant, okay, and T is the temperature in Kelvin. So here, temperature, please make sure that you always use temperature in Kelvin, okay, and also the units of the pressure and the units of the gas constants should be compatible. If the pressure is in kilopascal, then the gas constant should be in kilojoule per kilogram Kelvin, for example. Okay, and of course all units should be compatible. The second form of the ideal gas model, maybe this is the form that you are more familiar with, or this one. Okay, I see students, they are more familiar of this form, where n is the number of moles and r bar in these two is the universal gas constant, which equals to the gas constant divided by the molecular weight of the gas. And V bar is the specific volume divided by the molecular weight of the gas, or it's the molar based specific volume. The ideal gas model is an ideal gas, is an ideal model. So it doesn't provide good, approximation. Okay, or maybe it's better to say it doesn't provide the exact relation between the P, V, and T. But in limiting cases, and we'll see what do we mean by limiting cases in a few minutes. Okay, the ideal gas model gives justified, okay, gives good enough result. Okay, and we can check the result from the ideal gas model using the generalized compressibility chart, which we are also going to see in this lecture, inshallah. This is an example. I'm not going to go through it, but I encourage you to see it in the book. Okay, so go there, read it, and see how it's solved. Maybe I will just try to draw processes, because some of you asked me about how to draw the PV diagram. So here we have 1 pound of air in a piston cylinder assembly. So piston cylinder assembly is like that. The piston moves, undergoes thermodynamic cycle, okay, consisting of 3 processes. Process 1, 2 is constant specific volume, then 2, 3 constant temperature expansion, and then constant pressure compression. We saw similar cycle earlier, so this the first one sketch the PV diagram. So the first one is constant specific volume, so and the pressure changes from 1 bar, state 1, to state 2 of 2 bar, so the pressure increases. Therefore this is constant, so this is state 1, this is state 2, this here is 1 bar, and the pressure there is 2 bar, and the volume is constant. Okay, constant specific volume, so the volume is constant because the mass is constant, so constant specific volume means also the volume is constant. Then 2 to 3 is constant temperature expansion, and then 3 to 1 is constant pressure. So 3 to 1 will be this constant pressure, so this is 3, so this is 3 to 1, and 2 to 3 is constant temperature, which means that PV equal constant, equal mRT, and if the temperature is constant, then this is called a system, so mass is constant, R is constant, so this is all constant since the temperature is constant, as we said. So PV is constant means for ideal gas, okay, as I said before, this doesn't mean that it's straight line is wrong. This is how we draw isothermal or constant temperature process. Okay, so this is how we do Generalized compressibility chart. Let me talk about this in the next part of the lecture.